So, so with this lab, okay, remember the whole idea here was that we've worked on recognizing ionic versus covalent compounds with names, with formulas. So the one that you guys were looking at on Friday was you were analyzing some data, and we're going to really look at our data table right now. But you were analyzing data to see different properties such as melting point, solubility, and whether they are electrolytes or not, meaning they conduct electricity. And so with those properties, we're going to see hopefully today that we can chunk between the two categories as well. Okay, so each one has distinct properties. Just keep in mind there's always little exceptions, but those are things you learn later in the year. Okay, all right, so we're going to look at our data table. Okay, I'm just going to match mine up with yours real quick. So if you had any data that doesn't match what I say, you can just kind of single line cross out and then just put it next to it, or you can do a little like one of these and just kind of to show like get rid of it. I guess I should have done a diagonal. But show that you're getting someone else's data, not that that's what your data was, because you should always have your data. It should be raw. Don't fix it, okay? But I do want you guys to have good data, so just keep that in mind. All right, so you should have A, B, C, D, E, and then you had metal written in this last one, right? Okay, so for the descriptions, hopefully you described the metal, and then the other one should have been like white powders, or they should have been white crystals, or you should have seen white flakes, okay? So anything like that to kind of describe what they looked like. Order of melting, you should have had 3 for the top one. 1, none, 2, none, none. Okay, so real quick, what this is going to come down to is order of melting told us whether we had a low or high melting point. Okay, so low or high melting point. So a low melting point is something that like you can do in a school laboratory. High melting point is something that you have to go to a special one where you can get really, 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 really high temperatures, such as trying to melt that metal. We'd have to be in super high temperatures, right? So looking at your data that you've got, okay, which ones had the low melting points? A, B, and D, yes. Okay, the other ones are considered high melting points, okay? All right, and we'll come back to that kind of stuff later. All right, soluble in water, okay? So we're looking at solubility. You should have had yes, no. It should have alternated. Yes, no, okay? This one I know is tough. We're going off of visual, so just leave your data, but write mine off to the side. That's going to be the one that I want you guys to use so that you can actually see it. There's always room for error in these labs. You're going to see that with the conductivity part too, because any kind of contamination is always going to play a role too, okay? All right, but this is what we had. So for conductivity in water, what we're asking ourselves is it an electrolyte? And I do want you to write this word off to the top of it, or above it, okay, electrolyte. An electrolyte you guys have heard of in Gatorade, hopefully, right? Okay, or Pedialyte, any of those. So what those are is they have these little ions or these little they're able to conduct electricity, and it's something that your body actually also needs. And so we'll go into that in a minute. But so we're asking if it conducts in water. If it does, it is an electrolyte. Okay, so I'm going to try and use those words. All right, so for the first one, you should have had no. So this would be a non-electrolyte. Letter B should have been a no. Letter C should have been, sorry, I'm trying to remember what they were. I have them over there. Hold on. Oh, yeah. This one should be a yes. Letter D should be a no. Letter E should be a yes. And then for this one, I do want you to put no. Okay? Because what you guys did was you tested the solid, right? So you put both prongs on a piece of metal. So okay, so when it was asking if it conducts in water, it means did it dissolve enough to make the whole solution conduct electricity. All right, and so the water around that little piece of metal, it wasn't magically starting to conduct electricity because there was a piece of metal in there. It doesn't work that way. That's why I wanted you guys to have no on that one. Okay, but we're going to look into why it does when we look at what it looks like close up for metallic bonding. All right, okay, so using this information, we needed to break the things that were similar into two different categories, set A and set B. Okay, we're just going to go ahead and below set A and set B, we're going to write one for set C. You're going to write metal because the metal had its own set of properties and it's a different type of bonding. It's metallic bonding. Okay, so you can write zinc next to it. I'll just go ahead and reveal that one already too. That was a piece of zinc that you were dealing with. All right. So for or back up our data table here, we're looking for ones that have similar properties. So let's start with our low melting points. And then we see that these two are no's. That one's a weirdo and it's not saying that. And then over here we have no, 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 right? So we're going to leave A out because it doesn't match up with one of its properties, right? We'll come back and put them into one of the categories in a second. But if you notice, B and D happen to have similar properties. Okay? Now, if you reversed yours and you already started writing that one on set B, please don't erase it. Like, you're good. You do not need to switch it from me. Okay? Just keep them together. As long as B and D are together, you're good. Okay? All right. So we have compound B and D. The properties that we're going to list with it are what? Low melting point. We can say insoluble. Do we know what insoluble would mean?
It doesn't dissolve in water.
Right, so it's not soluble. And then are they electrolytes?
Yeah,
No, non-electrolyte. I know. All right, so that's for B and D. We'll come back and put A into one of these categories in a second. For set B, or the other one, you can put the ones that had higher melting points. Oops, sorry. Higher melting points. They did dissolve and they did conduct electricity. So we're going to put C and E in their own category. So one more time, they had high melting points. They were soluble. And they did conduct electricity. Okay. Okay, so now looking at these two categories, who does A share more properties with? Set A or set B? Who did you share? I would say set A, yeah. So we're going to add A, but we're going to give it a little star because we're going to say it was soluble. Right? That was the only weird thing. And we're going to see that sometimes those things fall into that category. We're also going to see some of set B type things that are not soluble. All right? So there's a lot of exceptions to these, but these are the general rules that we're grabbing from this data. Okay? So just general. All right. So, oopsie. My bad. Okay. So for set A, remember you have three things that you're writing underneath this, so just be mindful of how big you're writing. Okay. Letter B, was phenyl salicylate. Okay. And this little compound actually has a chemical formula of C9H7NO. So right off the bat, looking at that, okay, are there any metals? And C9H7NO. No, those are all on the right-hand side of the periodic table. Minus hydrogen, but hydrogen's not a metal. Okay? So what does that tell you from what we know about naming and looking at the formulas? What kind of compound is that? A covalent. I heard somebody say it. Covalent, right? Okay, let's look at, oh, I'm supposed to be showing you the pictures too. Sorry. There you go. All right, so that would be actually this one right here. And basically the way that these work is all of the little corners of these little, what shape is that? Hexagon? Yeah. All of those little corners are carbons, and these are just representing some double bonds and single bonds. And you can see that this whole little group of carbons connects to this oxygen, and it connects to another little group down here, okay? So if you're in AP Bio, you've probably started looking at some of those. But anyway, looking at that, you can see a distinct difference than the other kind of compounds. All right, so letter... Okay, so letter D was stearic acid, okay? And later, we're going to be seeing acids that actually do conduct electricity, are strong acids, and then even the weak ones slightly do. But this one, this compound right here, let me show you what that picture looks like so you can get an idea, is this one. Do you see this big chain of carbons? Lots of them, okay? And then just some oxygens and some hydrogens, or a ton of hydrogens, right? So looking at what this consists of and what you already know, what category does this fall under? Covalent or ionic? Covalent, why? There's no what? There's no metal involved, okay? So stearic acid is also going to be covalent. Finally, the last one that we threw into this category was A. That was just sugar. Okay, and sugar is, this is table sugar, so it's C12H22O11. Okay, and so looking at that chemical formula, and by the way, this one is sugar. Okay, so looking at that, do we see that that's also molecular or covalent? It's a big molecule, basically. Okay, so if you notice, these three categories, so the stearic acid, the phenyl, blah, 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 and the sugar, those are big molecules. They're just these combination of all these atoms just joined together with these lines. Do you guys see that? Kind of? Yes? Okay. All right, so we know set A represents covalent compounds. And we don't need to write anything on the lines below. I was going to have you do it, but it's good. We're good. Because we've basically already had a discussion on it. Okay? All right. Set B, let's go over who those guys were. Set B, letter C was potassium sulfate. So go ahead and write the formula because you should be able to do that. So you ask yourself the questions. Is there a metal? Yes. Is it a transition metal? No. So we would start with what we've already got. So potassium is K. We need to find its charge. So what is the charge for potassium? 1 plus 1. Good. And then we know sulfate is a polyatomic, so we look at our list, and what do we see? What is sulfate? There should be more people looking at periodic tables. What'd you get? Huh? But what's the formula? Good. Okay, and then she said a -2 charge. Then we take those two charges, we crisscross them. So K2SO4. Okay? So we got potassium sulfate. That was our first compound. And then letter E was just table salt or sodium chloride. So we're just going to write that. Okay? So that one was just table salt. And then metallic has their own category. So I do want to talk a little bit about set B, but what are we categorizing set B as? These are ionic. Good. So ionic compounds have those properties that we listed before. It's kind of off my screen now, so I can't really show you that again. But we have the high melting point, soluble electrolytes. Okay? All right. So you need to use these as another way to decide what you have. So if I give you a whole data table and I'm saying, hey, this thing conducted electricity when it was dissolved in water, what type of compound, or if I give you a list of compounds, you should be picking something that's ionic off of it. All right, so this is just another way for you to distinguish ionic covalent. Okay? All right, so I do want to show you, though, these pictures real quick. So this would be potassium sulfate. And basically what this is showing you is that, not that it floats around like this. That little drawing down there, that is showing you how they can go together, who's attracted to who. But an ionic solid or an ionic compound is that. It's that, all right? That one's a little overwhelming. So I'm going to take that one off the screen. This is sodium chloride. So basically what we're looking at with sodium chlorides are the big ones are the negative and the small ones are the positive. So basically your sodiums and your chlorines, okay? And if you see, they just alternate. Do you see that? So it's not just an Na and a Cl just floating around by themselves. These things have to be with this whole crystal lattice. This is what I meant by that. So now when we look at potassium sulfate, yeah, the sulfate part has to kind of stay together, but it exists as a big lattice. It's organized, they're all together, okay? Now the thing about ionic solids, you guys said that, do they dissolve in water? No. Ionic solids, you guys, come on. Do they dissolve in water? No. Yes. Yes, they do. So this is a little image kind of showing how that's possible. So basically what we're looking at is we have this whole crystal lattice and these little water molecules. So these are your water molecules right here. So this is your oxygen side. These two are little hydrogens. So as you can see, your oxygens get attracted to the sodium, and your chlorine or your hydrogens are getting attracted to the chlorines. And so these things just kind of get in there and they break this thing apart. Okay, it's called hydrolyzing. So that's how it's dissolving. So there's solubility right there. But what was the other thing we tested with that they are? Conductivity, right? So this is the reason for conductivity. Okay. It's because when they break them apart, and now you have all these water molecules in there, those things are holding on to their electron, or they're maintaining their ion structure, okay? And so now we have a bunch of positive and negative things floating around in water, allowing that electricity to flow through. If you look at these images, do you see that these are all little molecules? You see that? They're molecules, okay? Molecules, remember, things are bonding in the first place to kind of make each other neutral, right? So these things are a bunch of neutral things sitting in water. That's what you're kind of thinking, all right? That's not going to allow electricity to pass through, hence the not lit light bulb, okay? So that's kind of where these properties are coming from. I wanted you guys to see a little bit of the structure so that you kind of understood. The last thing I want to show you is this picture. What do you think this picture is representing? Who's the only one we haven't talked about? Zinc. Yep. So this is actually looking at zinc. Okay. What do you think all those positives are? Yeah. It's kind of like it's the nucleus. So it's like each individual atom is almost represented with that. And then now what we have are those valence electrons which are the blue dots, are they very organized all the way around? No, they kind of are, it's called delocalized, so they're loose, all right? And so all of these little protons are just letting these electrons bounce around. Therefore, can electricity probably pass through this? Heck yeah, okay? It's a flow of electrons, so yeah, definitely, okay? So this is where metallic bonding, this is what a metallic bonding is looking like. So if I had two different types of metals, it would still look like that, just with different sizes, okay? All right, so now that I've talked your ears off, look at this side. Let's talk about the homework, okay? So, so you should be able to answer number 3, 4. Number 5, I can show you up here with the little conductivity meter. So here's my conductivity meter. It's on. I'm going to pour some distilled water. Am I right? Okay. Pour some distilled water. And so you guys can kind of see that the light bulb is not lighting up. Do you guys see that? Okay. But if I take the tap water, so what's coming out of our faucet, and I put it on there, you guys are going to be able to see it. Can you guys see it? I see it. Okay. I know people in the front can see it. So it is lighting up. Okay? So why was it important for us to use deionized water? Of the conductivity test, right? So we were testing conductivity. If it already conducts it, then it doesn't help. Oh, look, it's sitting here. It's like on. There. Okay. So just make sure you have that written down for number 5. And then number 6 you should be able to do. So that is homework tonight for sure. It's due tomorrow. You guys will have an opportunity to knock out pretty much everything. So let me let you guys work on it for about 5 minutes, and then I got to show you one other thing. Okay? So 5 minutes. So we've already focused on the flowchart side. We're going to be focusing in on this side. So I just rotate your page so that you're looking at it like this, okay? And so basically, this topic is about bond polarity, all right? And I know polarity is like going over your head, but we're going to see that just like the Earth has a North Pole and a South Pole, like two different poles, that's kind of what polarity is. You have two different sides. One side is a little more positive. One side is a little more negative, okay? Or more like metallic character, less metallic character, even if they're both nonmetals, okay? And so that's what we're going to be talking about with this polarity. And so today it's specific to bond polarity. So as you can see, it says bond type. Right? And so we've kind of categorized these things as, oh, there's only two different types and that's it in black and white. It is not, okay? And so, so as you can see, you do have a big table full of a bunch of numbers, right? Where have you seen those numbers before? On your project, right? Didn't you guys have to analyze these numbers and look at which ones had higher electronegativity? This was your heart corner. This was the not so heart corner. All right. Okay. So that's where this is going to play a role, is when they combine who is pulling on those electrons. Remember, I told you it doesn't matter until bonding, really. Okay. And so, so now we're going to actually look at that. So part of your homework tonight is you will be not only completing the lab, because that shouldn't take you very long, but you're going to just answer 7 through 16 right here. All that you're doing is an electronegativity difference value. What kind of math is that? Subtraction. That is all you're doing. So you will literally look up phosphorus. So phosphorus is 2.1. Okay. And silicone is 1.8. So actually we will go 2.1 minus 1.8. Now, just because they're in this order as atom 1, atom 2, I would put the bigger number on top. I don't want any negative values, okay? So don't do any negative values. We're looking at the magnitude, meaning just what is the number value. So when you guys, if you have to plug them in, what do you guys get for this one? 0.3. So now we have to see what does that mean, okay? And I am giving you guys words that you haven't seen yet, but please know that polar and nonpolar are going in the covalent side, and ionic is still ionic, okay? You're going to see some covalent bonds act almost ionic, all right? But let's look at this side, because I want to give you the spectrum that you're going to be using, okay? So, and we'll do the questions above it in a bit. So number 4, you kind of have a little spectrum there, all right? And as you can see, I wrote 2 numbers for each of those 2 little spots. It's because it depends what resource you look at. It is not set in stone, all right? This is a very general thing. We kind of look at electronegativity difference and then also tie it in with the properties along with who's being combined. So that's why I put 2 different numbers. I don't care which one you use. This is really the one that I usually do, but I'm going to let you guys do that. So basically, once you've decided what the electronegativity difference is, now we can label it as one of those. So this one is 0.3. So we're going to go nonpolar covalent. Okay? Nonpolar covalent. You're just going to do that for all of them. All right? And this is, like I said, the last thing that kind of tells us what we're dealing with. Okay, so you guys have worked really hard on naming, formulas, properties. All of those can be used to figure out ionic or covalent. 2 separate categories. And then now we have electronegativity difference matters. Okay, for the bonds. Okay, easy enough? All right, that's it for homework.